we have another great fact.
I already have it.
Did that happen in the middle of the street in front of your neighbor too?
What?
Did that happen in the middle of the street in front of your neighbor too?
My background or my bee sting?
Oh, is that what happened?
Yeah, I had a wasp stuck in my shirt.
Yeah. That's not good. All right. So we're going to talk about the integral test today, but I wanted to do a quick recap of our topic so far because we've only gone through a couple of sections. Well, we've covered a lot of ground. So we started with a sequence. And we said our definition of a sequence is a function of the positive integers. And what we were interested in with a sequence, well, sequences are nice. They're just a list of numbers. To test for convergence, all we need is the nth term approaches a limit. Implies convergence. We also talked about associating, since a sequence where our definition is a function of positive integers, we can associate each term with a function value evaluated at that particular term. That's going to help us out with this process because we can apply what we know about limits of functions to limits of sequences. We also talked about the squeeze theorem. So if each term of a sequence is between the terms of two convergent sequences, they all have to converge to the same limit. And it's nice when you can apply the squeeze theorem and one of the sequences is 0. You squeeze the limit down to 0. We also talked about looking at the absolute value of each term. So if the absolute value of our terms, the limit as n approaches infinity, as the absolute value of those terms approaches 0, then the original sequence has to approach 0. So if we have some kind of sequence where the terms are alternating positive and negative, but the absolute value terms converge to 0, then our alternating sequence also has to converge to 0. Then we went into the kind of the base of all of this stuff. We talked about bounded and monotonic. And just a reminder for boundedness, we need to have an upper bound and a lower bound for our sequence to be bounded. And we also had a lot of discussion. An unbounded sequence can converge. A bounded sequence can diverge. All right, and then we jumped to talking about series. And remember, for series, we're adding the terms together. And for convergence of a series, everything that we talk about with convergence of a series has to do with the partial sequence of partial sums converging. And all of our tests are various tests that guarantee that the sequence of partial sums converges. We talked about some special kinds of series where we could find the sum. So we talked about geometric and telescoping. We can find the sum of these. We have a method to find the sum. For most of the others, there may be a method, but what we're interested in for the most part is Is there a sum? Does a sum exist? And then we talked about the nth term test for divergence. So our nth term test doesn't tell us about convergence. It can tell us about divergence. If our nth term doesn't approach 0, then our series can't converge. And then just a kind of big picture, remember we can delete a finite number of terms from an infinite series and it doesn't affect the convergence or divergence. All right, so let's talk about the integral test, our first big test for convergence. So our integral test, there are a couple of things that we have to be, there are a couple of conditions. So I'm going to say if f is positive and continuous and decreasing. So that decreasing part is what students often forget that we need to take care of. For x greater than or equal to 1. And we can associate terms of a sequence with a function value. Then the sum from n equals 1 to infinity of a sub n and the integral from 1 to infinity of f of x dx either both converge or both diverge. Yes.
Shouldn't that be f of n?
So what we're doing is the sum is discrete, but the integral is continuous. So we just let it be some variable x. And we'll talk about why we can make that comparison in just a second. And this could be, we could integrate. This should be n greater than or equal to 1. So n is 1, 2, 3, dot, 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 dot. X can be 1, anything between 1 and infinity, any real number. So the idea of why this works. We're not going to go into detail, but we can see the idea. All right, our function needs to be positive and decreasing. So our function is going to look something like this. So this is f of x, positive and decreasing. The value of the integral and the sum of the sequence, because the sequence is just this function evaluated at particular points. So I'm going to draw in some rectangles here. So I'm going to say this is 1, 2, and I'm going to do the inscribed rectangles, like so. 3, and I'll do one more. I know my rectangles aren't nice and uniform. 4. And we can go dot, dot, dot. And I'm going to go up here and do the circumscribed rectangles. So the value of the integral is between somewhere between the area of the inscribed rectangles and the circumscribed rectangles. And the sum of the sequence is somewhere in there also. So the integral puts a bound on the sum of the sequence, because the integral is somewhere between the area of the inscribed and the circumscribed rectangles. The sum of the sequence is just the somewhere between the area of the inscribed and the circumscribed rectangles. So the integral puts a bound on each term of the sequence. Sum of the series, sorry. It keeps the sequence of partial sums bounded. So the sequence of partial sums is bounded, and because our function is decreasing, it's monotonic. So the sequence of partial sums is bounded and monotonic. So that's the outline of why the integral test works. The integral puts a bound on this sequence of partial sums. Our function is decreasing, so that sequence of partial sums also has to be monotonic, monotonically decreasing. So our sequence of partial sums is bounded and monotonic, so our series converges. Now the part that we have to be careful with is, one, we have to make sure this is positive. This function is positive, and two, we have to make sure our function is decreasing. So just because you see some function and you think, oh, this would be easy to integrate, so I'm going to use the integral test, we have to make sure our function satisfies these conditions before we use it. So before I change the page, questions on our test? Yes?
Could we manipulate the series, so say it was negative and strictly increasing, could we manipulate it to look like it's positive and decreasing? So say it's just that function reflected over the x-axis.
You could make some kind of argument like that. So you could say, since this series converges, then the reflection in the x-axis over the x-axis would converge also. All right, so let me talk about a couple of things. One about this positive and decreasing. So what if you had something like this, some function, and you looked at the graph, and the graph of the function did this, something like that. So it's for x greater than 1. So here's x equals 1. It's not decreasing for the entire range, the domain of the function. Yeah,
Since you can just delete terms from the beginning of the sequence, you just move.
right. We just start here. We can delete a finite number of terms from the beginning of the series and not affect the convergence or divergence. So if your function decreases eventually, just start your integral test when it starts decreasing. So if you applied the integral test here and said, oh, this function converges because this integral from 1 to infinity converges, I would nitpick with you a little bit and say, well, the function doesn't satisfy the conditions of the integral test from x equals 1 to x equals whatever. How do we show that a function is decreasing? So one way that we can do it is show that a sub n plus 1 is less than n, or say a sub n, for n greater than 1. Now this is probably the more difficult way, but you can do it. One thing I want you to be aware of here is if you're trying to decide if a sub n plus 1 is less than n, you don't know that that inequality holds. So you can't work across the inequality. So what you have to do, you're going to say, if so, a sub n plus 1 minus a sub n has to be less than 0. So you have to somehow work with this, your two terms, a sub n plus 1 and a sub n, and show that when you subtract like this, that sum or that difference is always negative. That's how you would go about that. You could also say, or I'm going to say a sub n minus a sub n plus 1 is greater than 0, if I go the other way. But you have to somehow work with this quantity and show it's negative, or this quantity and show it's always positive. Yes?
Could you find a sub 1 if it was a positive integer, use the nth term test to find nth term equals 0, say it's decreasing?
You could do something like this.
Okay.
And then the integral test wouldn't apply basically for the entire thing because it's not decreasing for the entire time. Yeah.
Could you just take the derivative of the function?
That's the other way, and it's usually the easier way with the integral test. Depending on the function, sometimes it's a little tricky. You have to do a little tricky math. You could say f prime of x is less than 0 for x greater than or equal to 1. So you can take the derivative and show that the derivative is always negative. That would show you that your function is decreasing. Now sometimes doing the algebraic manipulation with your derivative to see that it's always negative can be a little tricky. But either of these ways is going to be an acceptable way to show your function is decreasing. So when you apply the integral test, make sure that you ensure that your function where you're applying the integral test is positive and decreasing. All right. Let's look. I just want to go through an example. And let's see. There we go. And this is nice because we'll get to remember how to do improper integrals. N to the fourth, yes. All right. So we want to test for convergence. We want to decide if this thing converges. So our first question. For x greater than or equal to 1, is f of x equals x over x to the fourth plus 1, is that positive? Right, there's nothing to make it negative. Is it continuous? Yeah, we don't have any divide by 0 problems. So it's a nice function. Now we need to test if it is decreasing. That doesn't. To apply the integral test, that's kind of the same question that Ben asked, because the function could be doing something like this. and then it wouldn't, then the integral test wouldn't apply, even though the nth term is approaching 0. So let's take the derivative. We're in a calculus class. We like to do calculus. So f prime. We get to use the quotient rule. X to the fourth plus 1 minus x times 4x to the third over x to the fourth plus 1 squared. So my key here is going to be try to show that this numerator, this is never going to be negative, to show the numerator is less than 0. So I'm going to multiply this out and simplify. So I get x to the fourth minus 4x to the fourth plus 1 over x to the fourth plus 1 squared. And now I get a minus 3x to the fourth plus 1 over x to the fourth plus 1 squared. For x greater than 1, is this always negative?
Yes.
Yes. This is less than 1. Sorry, less than 0. Greater than or equal to 1. So sometimes when you do this, doing that derivative to show that that quantity is always negative can be tricky. Or to see that it's always negative can be tricky. All right, so we're good. We can apply the integral test. Yes?
If you were to do just, if you were to show that a sub n plus 1 is less than a sub n,
Mm-hmm.
could you just do like one example?
No.
So you can't.
Yeah, you'd have to somehow show that it's true for every possible value of n. So you end up doing something like this. You do some manipulation and say this quantity is always negative.
Okay.
Yeah. All right, so let's integrate. So we need to find the integral from 1 to infinity of x over, oh, this is a nice integral too. What do we want to do? U is x squared. Du is 2x dx. So we have the 1/2 the integral of du over u squared plus 1, which is 1/2 inverse tangent of u plus c. This is an inverse tangent integral. All right, so we're looking at this improper integral. For an improper integral, the limit as b approaches infinity, the integral from 1 to b, because we can't evaluate an integral at infinity. Infinity is not a number. We have to approach infinity. In fact, a lot of students have a hard time visualizing how big infinity is. So here's how we visualize how big infinity is. Think of the biggest number you can imagine. Everybody have a number? Yeah.
5.
That's not it.
Is it bigger? That's not it.
All right, so we have the limit as b approaches infinity of 1/2 the inverse tangent of x squared. And we're evaluating that on 1 to b.
C.
So this is 1/2 the limit as b approaches infinity. This limit as b approaches infinity is a part that most students don't like, of the inverse tangent of b minus the inverse tangent of 1.
It's B squared.
b squared
C.
and 1 squared. Just to make Dylan happy.
It's like b squared, infinity squared.
All right, so now we need to know we need to remember our inverse trig functions. As b approaches infinity, what does the inverse tangent of b approach? Pi over 2. Very nice. Remember, your inverse tangent function looks like this? And it has horizontal asymptotes at pi over 2 and negative pi over 2? Minus inverse tangent of 1. What angle gives us a tangent of 1? Pi over 4.
Okay. See, I'm more efficient by now.
Here, I realized that's
And
the
my
number.
space use.
Say,
That's less than infinity. That's finite. So our series converges.
Could you also say the other angle that equals tangent of 1?
Inverse tangent, we have to, we only get angles between negative pi over 2 and pi over 2. Because we have to restrict the domain of the tangent function to have an inverse. Yeah.
What if your function was like sine instead of tan inverse? How would that work? Like, what is that?
It would oscillate.
Well, it would be somewhere between positive 1 and negative 1.
Could you still say it converges?
Yeah,
Okay.
yeah, because that's a finite value.
So as long as it's not infinity.
As long as it's not infinite, as long as it's a finite value, it converges.
So how would you write that? Just
Let's inverse sine of
normal sign, like since that's oscillate, you would just write that as a finite value.
right. It's a finite. It's between. Yeah, it's between 0.
It has to be greater than
Right.
1 times
Right.
whatever it was.
Now we cannot. Here's where we have to be careful. We cannot say that the sum is pi over 8, because this evaluates to pi over 8. The value of the integral and the value of the sum of the infinite series are not necessarily the same. In fact, they're usually not the same. In fact, they're almost never the same.
But sometimes it might be.
Sometimes they might be. Yeah, it would be nice if the value of the integral was the sum of the series, but that's not the way it works out.
Why though?
Dang.
Because all the integral does is put a bound on the sum. It doesn't give you a value of the sum. All right, so questions on the integral test. So as you might guess, that the integral test gives us two things. It gives us some practice with improper integrals, and it gives us a reason to do some more integrals, which is always a good thing, right? Okay. And next time after the quiz, we will apply the integral test to P-series. What's that?
P-series go with the at the term test, right?
No,
Like
P-s-
requirement to be demonstrated with the actual term test. That's the harmonic series. Is
P equals, so the harmonic series is P equals 1, but we use the integral test to prove
and that's the
that when the P series converge.